So problem here, C10H13NO2. First thing you do is the degrees of unsaturation. So what is that? All right, so the number is 5. So immediately we're thinking, ding, 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 probably benzene ring, right? So probably benzene ring, which of course is worth 4 degrees of unsaturation. So we still have one more to go. So we need to think about a pi bond or ring at some point part of the here. Okay, so next thing, let's look at the IR. So the IR tells us 3285. So we have 3 stretches in the IR. We have one at 3285. So that could either be a couple things. So usually I would tell you it's broad. So it's either probably an NH or an OH. So we'll write NH or OH. We don't know. Right? It's tough because this has both nitrogens and oxygens. So who knows? 1659. What do we think that could be? C double bond O. And do we have any idea, any ideas of what kind of C double bond O it might be? What's in that area, that region in our tables? 1659. Ketones are at 1710. 1659 is amides. Right? So amide. So we're not sure, but who sees? What about 1246? What's that? Yep, 1246 is CO single bond. Okay? So that gives us some information, but it's not all the information. Okay, so here are the NMR stretches. All the NMR stretches here. So what this is telling me, essentially all of these, we have 1, 2, 3, 4, 5, 6 types. Right, so 6 peaks. Some of them are coupled to each other, some are not. So we'll start breaking these pieces down now. So let's see. So the first thing I look at, I know we have a benzene ring, and I don't know how many substituents I have off it. So that first benzene ring piece, obviously I have one thing off the benzene ring, but the other question is how many other things do I have? So to figure that out, I look at the benzene ring region and see how many hydrogens are there. Now be careful, this one at 7.5 is a broad singlet, right? So it's fat. So that would tell me it's an OH or an NH, not really has nothing to do with the benzene ring. It's an OH or NH. So in the benzene ring, I have 7.3 and 6.9, each one with 2 H's. So I have 4 H's total in the benzene ring. So how many substituents do I have in the benzene ring? 2.
Wait, can you go back?
So I have 7.5, broad singlet, that's an OH or an NH. It's broad singlet. The other two at 6.3 and 7.3 and 6.9, that's in the aromatic region. And there's 2 H's for each of those. That means I have 4 total aromatic H's. So that means I have 2 substituents off the benzene ring. Now the question is, where do I want to put that substituent? So I have 2 types, and they're both doublets. That should be a key for you to recognize, they're para-substituted, that 1,4 substitution. So I draw H, 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 H. So I'll call one of these B and the other one C. So I can check off B and C. I don't know what A is yet. I don't know if it's an OH or an NH, so I'm still going to wait on that. I'm not sure.
But you can say that those hydrogens are on the benzene ring because of the...
I can say they are because where their frequency is at. 7.3, 6.8. Yep. So I subtract that piece out. So if I have C10, H13, NO2, I subtract out C6H4. So C4, H9NO2. Good. So now the next thing I look for here, I would look for things that are coupled to each other. Like these two, B and C were coupled to each other, which makes sense. That means they have to be 3 bonds away. And it looks like D and F are also coupled to each other. We got that classic quartet triplet, 2H, 3H. So that piece would be to me then, I would guess, it's at CH2, CH3. Right? And they're coupled to each other, so I know they're 3 bonds away. So the 2H, we have that label as D, and then CH3 as F. So we can check off F and D. So subtract that from our formula. So that's going to be minus C2H5. So C2H4NO2 is what we have left over. Now what else do we have? We have E. It's a 2.13H. It's a singlet. So that's probably a CH3 with no nearest neighbors. So we can draw that piece right here. Make that E. All right, so we can check off E. So let's subtract minus CH3. So it's CHNO2. So now we got to make that tough choice. So now we got to decide, what do we have? Well, if we have an amide, which we kind of thought we did, right? So let's make the leap and decide that's one of our pieces. That amide is one of our pieces. So there we subtract what? Minus C, N, and an O. So we have an H and an O left over. Now you get cautious here. Some people want to automatically go to OH, or maybe you're kind of stuck here. So now let's go look at the frequencies. So one of these frequencies should stick out to you. The one at 4. Right? If you're at 4, what are you probably bonded to? Are you bonded to a nitrogen, an oxygen? Are you allelic? What are you? Probably bonded to an oxygen. So I'm going to take this oxygen and put it next to D. Where was D? D was right here, right? So I'm going to say there's an oxygen here. I don't know what else is bonded there, but that takes off that minus an O, right? So now I have an H. So at this point, the OH-NH brittle should have been solved. Because if I put an H here, then I'm done, right? I can't do anything else. The only place I could put the H that makes sense then would be on the nitrogen of the amide. So I'm going to put that H here and label that A. So we can check off that piece. If I attach to the O here, then there's an OH there, and how many bonds does oxygen want to have? 2. And then I can't attach it to anything else, right? So don't forget those basic things. Carbon wants 4 bonds. Oxygen wants 2. Nitrogen wants 3. Don't break those rules. So if I put the H here, then I'm done. I can't connect these other pieces, so that obviously can't be right. So now at this point, try to fill in the blanks. Okay, so at this point, hopefully we're working on figuring this out. Get this up even smaller, get it out of the way. Maybe blow this up again. Right, so what do we need? So I think that nothing else can be bonded to the oxygen. If something else was bonded to the oxygen, the thing would stop, right? And we usually don't have ON bonds. Oxygen doesn't bond to nitrogen. Don't do that. So the benzene ring for sure is going to have this O, CH2, CH3. Now the question is over here, what else is going to be attached? How are these last 3 pieces? So if I've checked off this piece, right? How am I going to put the CH3, the amide on the other side? Look at the frequency. E is at 2.1. What range is that for? 2.1. That's allelic. So you have 2 spots to choose. Either it can be bonded to the nitrogen, or it can be bonded on the other side of the carbonyl. If it's bonded to the nitrogen, where would you expect it to be at? If it's bonded to the nitrogen, where would it be? 2.5. Is it at 2.5? No. Let's put it next to the ketone, like a allelic position. So that means the nitrogen is going to be connected to the benzene ring. All right, so labeling. This would be proton E. This is proton A. One of these will be, make those ones B. These ones C, D, and F. So the common mistake people do, they want to put the ethyl group on the nitrogen, but if it's on the nitrogen, it would be at 2.5, not 2.1. So it's right in the allelic position. So this is the right answer. But that's a common one people will try to do, is do it that way. Okay? Good. All right, working a new problem. C10, H10, O2, and the degrees on saturation would be 6. So again, we're thinking benzene ring. Ding, ding, ding. Benzene ring. Right? But then we have 2 more pi bonds or rings, some mix of that as well. IR, they're saying, pretty short here. They're saying IR 1681. And they're saying no OH. Okay. So if 1681, what could that be? 81. What range is that in?
1681. It's too high.
So it's some sort of carbonyl for sure.
It could be a CO bond, a C double bond.
So it's definitely C double bond O. And do we know what type? You might say amide, but are there any nitrogens here? There's no nitrogens, right? So it's probably next to the ring, right? Because of resonance and making that more single bond character. So even higher level, you could say conjugated. Right? Question mark? I don't know. But that's pretty low and it can't be an amide, right? Okay. Let's look at the NMR. So a couple things to look at here. It's C10H10 and you have only 2 peaks in the NMR. That should tell you what? Symmetry. Very, very, very symmetrical. Let's look at the first peak. 2.82, 6 H's in the singlet. So can a carbon have 6 H's bonded to it? No. So that's probably 2 CH3s. So it's probably 2 CH3s. These are A, 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 A. 2 of them. C10, H10, O2, C2, H6, C8, H4, O2. Peaks at 8.13, 4 H's and a singlet. So we know we have a benzene ring from the IR. Well, from the degrees on saturation. What kind of substitution? So we always have there's one thing on the benzene ring. But if I have how many total H's in the aromatic region? I have 4. So it's going to be what kind of substitution? Di substituted and where? On the other end, right? But now there's another wrinkle here. It's a singlet. That means what? What does that mean about all of these H's off this ring?
They're all the same.
They're all the same.
Yeah.
So what does that mean about the things that are coming off the ring? They have to be, right? Whatever this is has to be, these 2 things have to be the same. Right? The 2 things coming off the ring have to be the same. So let's subtract that piece out. C6, H4, C2, O2 is what we have left. All right? So now we're kind of stuck here because we've checked off our A and B. Remember back here, our degrees on saturation was 6. The benzene ring covers 4 of them, so we have 2 left over. And we thought we'd have carbonyls, right? How many carbonyls must we have then? 2. And it looks like C2O2. So the other piece left would be, right, 2 carbonyl pieces. So now we have 1, 2, 3, 4, 5 pieces. There's only one way this actually can go together now. But you could also look at the frequencies. So at this point, there is only one way to put it together, but you can always go back and check the frequencies. So 2.82 is what region? It's a little bit higher than the allylic, but where does it have to go? Right? If I put the CH3s here, if I put A here, I'm stuck, right? You have to put the carbonyls on either side and then the CH3s on the other side. All right, so the final answer looks like this. So our final answer then, highly symmetrical. HA, we're 6 singlet, more or less a little bit higher than normal allylic region, but it's all part of this system. The ketone would have a lower number than usual because it's conjugated, right? So it'd have more of a single bond character, so it would go at a lower frequency. That makes sense. All these HBs are the same because everything's on the same on either side. This checks out. So working on a problem here about essentially labeling on an NMR spectrum where the peaks would be, what the splitting would be, what the frequency would be, and how many H's they'd be worth. So the hardest part with this one is, I think, just drawing this correctly. So if I draw it in a stick figure form, I have a CH3 bonded to an O, which is bonded to a carbon, which is bonded to 3 CH2s, right? 3 CH2s, which are bonded to O CH3s. All right, so if I number these carbons, there's 1, 2, 3, 2, 3. In this piece is CH2O CH3, CH2O CH3, and we have 3 of them. So there would be your pieces. Highly symmetrical. Draw in the types of H's. How many different types of H's will we have in this molecule? Look at that, see if we can figure that out. How many different types of H's? So we'd have 3 types of H's. I'm going to label them A, B, C. So A is worth how many hydrogens? 3 hydrogens. What should its splitting be? Singlet. Very good. B is worth how many hydrogens? 6 hydrogens. What's the splitting going to be? Singlet. C is worth how many hydrogens? 9. The splitting is going to be a singlet. Very good. Now let's go back and look at the frequencies. They really all should be essentially almost the same, right? They're all next to those oxygens, but maybe the one I would say, maybe the B, if you had a guess, these CH2s are kind of really surrounded by oxygens, right? You see how these CH2s are maybe feeling it a little bit more than everybody else. So I would guess the CH2s, like B here, would be the most deshielded, right? And then the next one, I don't know how you can tell between A and C, and I think they're a little more forgiving in sapling. But I would guess B would be the most deshielded because it's kind of stuck, right? It feels this oxygen here, while it also feels all those two as well. So I think B would be the most deshielded. So that was the trick. They're all singlets, the right number of protons, and then the hard part was that B was the most deshielded. Okay, working on a problem without a molecular formula, they just give you the mass to charge ratio, so they give you the molecular mass, and they're saying it has a mass spectrum of 2 molecular ions. 2 molecular ions automatically makes you think of bromine and chlorine. And they say it's at 180, 182, so it's an M and an M plus 2, so still good. But it says they're equal intensity. So if it's equal, that's bromine, right? Bromine's 1 to 1. Chlorine would be 3 to 1. Good. So we're going to say here, this is telling me bromine. So I can take 180 and subtract out the normal one, like 79 from that. So I have 101 left. So I know I have one of my pieces already, I know, right? Bromine is alive and well. Bromine has 1 bond there. That's what it's telling me. The IR, sadly, only shows us 1 peak, 1740. So what does that tell us? What could that be? So we know it's what? C double bond O. Any idea what type? So it could be an aldehyde or an ester. Good. So we're going to say ester or aldehyde. Now, I'm already being suspicious of the aldehyde choice. Because if I did an IR of an aldehyde, what other stretch would I have? I would have a CH stretch, right, at 2820 and 2720, the aldehyde CH. I wouldn't not give you that, right? That's not really fair, right? So I knew it was ester aldehyde because if I look at my table, 1740 falls where esters and aldehydes fall in the IR table. But I'm going to guess it's probably not an aldehyde. And if I look at the NMR, where would I expect to peak at in the NMR for an aldehyde? Where would I expect to peak at in the NMR? 9 and 12. And I do not have a peak any higher than 4.36. So I'm saying no to the aldehyde. I'm thinking ester now. I'm thinking ester. Alrighty. So 4 peaks. 4 peaks here. And they all have the same coupling constant. Oh no. Can they all be coupled to each other? Could all 4? No, they can't. So they have the same coupling constant. That's just well, it just happened. Okay? So but we can still figure out who's bonded to who. It's actually pretty easy. Let's look at A. So A is 1.30. Right? Let's look at A. A is 3 H's, so that's probably a CH3. Right? A is probably a CH3. How many nearest neighbors does A have?
Has two.
2. Right? A has 2 nearest neighbors. So at this point, you have HA, and we said HA is a triplet, so it has to have how many nearest neighbors? 2. So which one is it going to be? Well, I look at my options. There's only one of them, right? This is where B is worth 3 H's, C is worth 2, and D is worth 1. So it has to be C, right? Because it has to have 2 nearest neighbors. So HC and HA are talking to each other.
And then C has to.
So then, if that's the case, that means B and D have to be talking to each other as well. So what does B look like? B is a CH3 as well. But B is what kind of splitting? Doublet. So how many nearest neighbors does B have then? 1. And that nearest neighbor is D. HD. So we can cross off those 2 pieces. So let's go back to our molecular formula. 101 minus C2, 24, plus 5. What's 24 plus 5 is 29. 0, 1, 9, 11, 2, 72. Another piece is C2, 24 plus 4 minus 28. 44.
Wait, 29 was B and D, right?
29 is A. 24 plus 5 is 29. 24 plus 4 is 28. So we have 44 left. Okay, so we have 44 left, and maybe at this point we're kind of stuck, right? Because we're done here. So let's go back to the IR now and look and say, well, we talked some about an ester. Okay, let's draw ester as a piece. All right, we don't know what's on the other side of that. How much mass is an ester? Like carbon is 12, plus the oxygen 16, 28, plus 16 is 44. So minus 44. Good, we're checked off. So now we have all our pieces. So let's circle our pieces. We have 3 pieces. Now at this point, there's actually only one way this can work. You can go back and look at the frequencies to make sure it makes sense. So let's look at something that's...
I thought we had 4 pieces.
Oh, I forgot the bromine.
Yeah.
Bromine. There's my bromine. Bromine's right there. Right, so now we got to find out how we want to make this work. So take some time and try to do that. So you should have came up with 2 possible answers. 2 possible answers. And one is right and one is not right. This is actually the correct answer. So once you create a possibility, go back and look at the frequencies. So HC need to be at 4.23. If HC is at 4.23, these 2 CH2s, that's way de-shielded. As you have it right now, it's in the allylic region. So that can't be right. Right? That can't be right. Also, HD, if you were HD, you have it at 4.37. If it was 2 bonds from an oxygen and a bromine, it's probably going to be way more de-shielded than 4.37. It'd probably be up around 5 or 6. So that's the best way to know that these don't work, right? The splitting works, everything works, the splitting works, the numbers work, but the frequencies don't match up. Now if you go over here, HC, 4.23, makes sense that's next to an oxygen. D, both allylic and next to a bromine, 4.37 makes sense. That's in the right area. So the answer here is this one. But this is a possibility, but you gotta go back and look at the frequencies. The last thing I usually do is look at the frequencies to make sure it makes sense. Way to double check.